record the video. Take care. So let's see, what do we have? That is just the inner product. And today we are going to use this inner product property to derive some equivalent format for the AX equals to B, that is the linear system of equation. And let's see how can we get a equivalent system for equivalent format for this linear system of equation. So there's one theorem we want to prove today. So let's see, there's one theorem, and all the things I am mentioned here, it should be from the textbook 1 and textbook 2. And so this one is from the textbook 1. And you can just go back to take a look which one is the textbook 1. And it's on the textbook 1, theorem 7.31. And this theorem is saying that, so if the vector, so we are giving equivalent format for the linear system AX equals to B, and then this is the theorem all these theorems about. And so let's say the vector X star and is a solutions to the system, the linear system AX equals to B, where A is positive, definitely. Then this linear system equation AX equals to B, and it's equivalent to, so this is a solution, and if and only if this X star satisfies the below, so X star is the minimal X star produces the minimal value of the following function, and then the following function is defined in this way: gx and equals to the, so this bracket here, it means the inner product, and then we define the inner product in the last class, and we use the curly bracket to indicate this is the inner product. So now this function gx is defined with the inner product. So we have a vector x here, and we also have the matrix vector multiplication, and then so this ax is still a vector, and we do the inner product between them and subtract the two inner product between the x and b. So this means that if x is, so this theorem is saying that if x star is the solution of this linear system, if and only if x star produces the minimal value of this function. So this is the theorems we want to look into. Any questions before we move on? The theorem statement. Okay, so if you don't have any questions here, let's see what do we have next. So we are going to prove this theorem because this is very important, and then I'm not going to skip this, the proof of theorem, but we have a lot of theorem in this chapter, in this section. So I'm not going to skip this one, but I'm going to skip several theorem proof later on. So, but this one is very important, and then you need to master it. Maybe for your exam, for your final, I don't know. You need to master it. This one is so important. So let's see the proof. So let's say we have fix x and fix v, v vector. So let x and v. So we have the x vector, and then the v is non-zeros, be a fixed vector. So starting from here, we are going to get some functions about the gx. And we have a t, which is a real number here, a real number variable. And let's calculate this functions. And we calculate this function, gx, x is a vector, and then plus the tv. And you will see I am only here. Here you will see that this one, the x and v are fixed. And then the only things is changing is the t variable. And the t is a real number. And now let's see, let's calculate this. So what is the gx function? Gx function is defined in this way. So let's just substitute the x plus tv here, and then ax plus tv here, and subtract that 2, x plus tv, and then b here. So let's just expand the whole things here with the property we have here. You have the associated law. So you can distribute the things to the y, and then in the product with the y, and then we can do the sum later in the product. And we also have the scalar property. And let's see, and we also can switch the positions of the components in the product. So we are going to make use of these properties to calculate the expansion, do the expansions here, and then we got, okay, so we have ax. So I'm going to multiply this out. So this one is just the x, and then multiply the ax. And then the next, I'm going to multiply the x. Let me see. Let us just do one by one. And then I prefer this way, x multiplied by ax, and then the next is x multiplied by atv. And so I got x and then atv, but the t is a number, so actually we can just get this one out from the inner product parentheses. Next, I'm going to focus on the second component, and then this is the tv multiply the ax, and then I got t and v and ax, and the tv, the second component there, and then multiply the atv, I got t squared and then vav, and this is because the components I have here. So this one I have tv multiplied atv, and then I got 2t here, so I got t squared and vav. And next, I'm going to expand this parenthesis here, the inner product here, and then let's see what do we have. And I have 2xb, and then minus, and then once again there's a real number t, and then I have vb. Okay, so and that's the things we have. Let's collect all the things about. So now let's see. The yellow part, that is the x and v. X and v are fixed number, are fixed vectors. And the t is the only variable here. So now let's view this function as a function of t. So what do we have for the constant? What do we have for the first order term? And what do we have for the second order term? And let's see. So the first order term, so we just have the t, right? And so this is the first order term, and this is these are the first order term. And let's see. So the constant term we have here is the XAX and the minus 2XB. And we have one more thing here is T variable. And this is also the first order. And let's see, and then the second order, we have the T square. So if you take a look at the constant term, and then you will have this. The constant term is the XAX, subtract the 2XB. And if you look at the GX function definition, and then the constant term is just the GX. So we have, for the constant term, we have GX. And for the term we have here, we have the T variables, and then we got plus T. So first we got T, and then we and AX subtract the 2B. And but if you take a look at the property of the, if you take a look at the property of the inner product here, let's go back to here and then to investigate one more property about the inner product. So if we have a matrix A is symmetric positive definite, symmetric positive definite, and then let's see what happens to this. So we have the X times the inner product with AY, and it equals to, so by the definition of the inner product, it's just the X transpose, and then and X transpose, and then times the AY. And if we do one more things here, and then we got, because the A is positive definite and the A is symmetric, and then we got X transpose equals to A transpose Y here. And let's see, this equals to, so X transpose times the A transpose, it equals to AX transpose, and then equals to Y, multiplied by Y. And this equals to AX Y. Does that make sense? So we have a conclusion that X AY equals to AXY. So by the definitions, this inner product is just equals to the X transpose AY. And because this is symmetric, and then we have the A transpose equals to A here. And this one, if you use the transpose property here, the X transpose A transpose is just equals to AX transpose, and then times the Y, and then it equals to, by definition of the inner product, we have this equals to AXY inner product. So you can see for this inner product here, we can move the A matrix to the component A here. So we have the AXY here. So let's go back to the things we have in the proof. And so let's see for this component, what do we have? This component here we have, so it's just equals to T and then AX and then V. And it also, because we also have one property, because we can switch the position of the inner product here, switch the component positions here. So for that component, for that that turns here, we can also switch the positions, and then we got T and then V AX. So at the end of the day, you collect all the items with the first order T, and you will have T. So T, and then we have the V AX plus AX, and then subtract the 2B. And so you got what do you get at the end? So there are 2ax here, subtract 2b, and so at the end you actually get 2t here, and then ax subtract b. And this is the first order t term. And then let's see what is the second order term here. The second order term is the purple one. The second order term is the purple one, t squared, and then we agree. And as you can see here, we have a function of t here, and then the gx is just a number, and then after the inner product is just a number, and then with 2t, t is a variable, and then after the inner product, this is also a number, and then this is a t squared variable. So this is a function of t, and let's see what happens here. So let's say this is a function of t, and we define it in this way. So this is the ht, we define a function of t by letting the ht to be the gx plus tv, and then where the x and v are fixed. Any arbitrary vector here in the space, and then but x, but the v is non-zero. And now let's say this is a function of t, right? And let's say we want to minimize this function. And if you want to minimize a one variable function, and then what would you do? What would you do to get the minimum? Getting the first derivative, right? And then the critical point, right? Yes, let's do that. So let's do the, let's get the minimum value. So because here, this is a positive definite function, right? This is a positive definite matrix, and then the v is a non-zero vector. And what gives us that? This gives us that this number is bigger than 0. So the ht function is actually a quadratic function, and then it's open up. So this, you see that this is a positive, this is a positive number, and then this is t squared. And usually we get the curve looks like this. And this is saying that we have a minimum value. And so let's get the minimum value of this ht. Get the minimum value of the ht. Minimum value of ht. And so first, let's get the first derivative of the ht. And we got, so the first term is just a constant about the t, so that is just a 0. And then the second term here, we get, if we get the derivative of the t, and then we get the function, the value should be ax minus b. And then for the second term here, if we get the derivative of this term about t, and then we have 2t, and then this is, you can treat this part as a constant. So we just write that down, and we get the 2t, and then we agree. And as we just say, we want to get the critical point, and which means that we want to let the h prime t equals to 0. And that's the things. And we got, what do we have here? We have the t equals to the v bar, and then I'm going to change the sign here, ax minus b, and then if I change the sign, and then that is the b minus ax, and this is the solutions for the h prime t equals to 0. Any questions here? Because this is a quadratic function, and then it's opening up, and so this critical point should be the minimal value. It produces the minimal value here in the ht. What does it mean? It means that if we are given a function, So what does it mean here? It means that if we in the space we have here, and then we are going to get the minimal value of gx, and we choose a fixed point x and a fixed directions v, and this is the x, and then this is the v, and in these directions you will have a minimal values in these directions of the gx function, and then that point you should calculate by the t given below. So let's say this again. So this is the minimal, this is the functional we want to get the minimal value, right? And there's a space here. This is the space here, and then we have the x and v, and then all the vectors here. And then if you choose a point x, and then you choose a point, a directions of v, and on this line or on this directions, and then you would get a minimal value of the gx. And then the minimal value here, it should be the x plus the t hat v. And what is the t hat here? Let's say this is the t hat, and this is the minimal value of the ht function. Does that make sense? So we are calculating the minimal value of the gx in one direction, in one fixed direction, and then if the x point is given. Any questions? So you haven't decided the x vector yet. You haven't decided the v vector yet. But if the v vector is given, and then in this direction, you can get the minimal values on this line by using the t value here, the t hat value here. Any questions?
The serum does it need to be symmetric also?
Symmetric. A positive definite, we usually define the positive definite based on symmetric.
Oh,
yeah. So this is not the end of the proof, because this is just one direction. You're giving one on this whole space, and then you are given one vector x, and then you're given one direction v, and then you are calculating the minimum values on this line of the gx, and this minimum value is attained at this point x equals to the so this is the x tilde, this is the minimum value of the gx along this line, and then this x tilde equals to x plus the t hat, and then v, and this is the first part of the theorem, the proof of the theorem. But next part we are going to prove the whole theorem. That we say it's actually in the whole theorem that we are saying that ax equals to b if and only if x star produces the minimal value. So let's take a look at the second part of the proof. So this is just the minimal values along this line. And so let's see, okay, we have a t hat, and then let's substitute back to the ht function. So we have the ht function, and let's substitute the ht hat back to the let's substitute the t hat back to the ht function, and we got this is just a gx plus t hat. This is the definition of our ht function. It's defined it with the gx plus tv, and then now we just change the t with the t hat, and so now we got this gx, and then subtract the 2 t hat. This is what we calculate just now. v b minus ax, and then plus the t. This is the second order term, v a v. And let's calculate this, do the substitution gx. And what's the 2t hat? The t hat here is the v b minus ax, and then v a v, and v b minus ax, and then plus, what is the t squared? T squared is just a b ax, and then v a v, and then all the things taking the square. Okay, is so big. Okay, and the next thing is the v a v. And you will see at the end, you do some simplification, -2 and then +1 item of that one, and then it gives us subtract just one item, v b minus ax, and then taking the square of this one, and then v a v. You will find that after some simplification, these times, this one is the same as this one, but this one is one with the coefficient 2, and this one is with the coefficient 1. So we do the subtraction and do the sum with this one, and then it gives us just subtract one of the items. And this is the HT hat, and that is the minimum values on this line, along this line, the gx function. And let's see. So what does it mean by here? So it means that if you take a look at this one is always positive. I just say that A is a positive definite matrix, and then V is non-zero. So this one is always positive. And this one is always non-negative, right? Because there's a square here. So let's compare this one, the right-hand side here, to this one. So x plus t hat v is just the g function's value at the possible minimal value point. And gx is this point. It's the g function's evaluated at this point. So what does it mean? The minimal value is equals to the gx value here, and then subtract by this value. And let's see, if this one equals to 0, we for the vector v, and then we have the b minus ax, and then do the inner product, it equals to 0, and then this number is just equals to the minimum values along this directions. So we have a conclusions here. So from this point, and then we have, so for any vector v that is non-zeros, we have the g x plus t v is less than the gx unless we have this, unless we have the v bax is equal to 0. And then if we have the v bax equals to 0, and then we have the gx is just equals to the minimal point. And so let's see, let's get this into details. So what we have stated in the theorem is that if the gx, if the x is the solution of the ax, and then we have this, and then because this is the if and only if statement, and then which means that if this is a minimal value of this function, and then we have this is the solution. So we are going to prove both ways. And so first of all, we assume that, so first of all, this is the directions 1, and it's going by this way. So if the ax, if the x star is a solutions of the ax equals to b, and if this is the solution of the ax equals to b, and this means that This means that the AX star subtracts B subtracts the AX star equals to 0, right? And this also means that for any vector V, which is non-zeros or 0, it doesn't matter. So for any vector V, we have this inner product equals 0 because the X star is the solutions of the AX equals to B, right? And now by the functions here, so we have, so this means that the GX plus T hat V and then equals to the GX minus the VBAX. I just summarize all the things here. VAV. And so by this function here, by this equality here, because now for any vector V, we have distance going to 0. So this is for any vector V, because now we have this equality. So for any vector V, we have this is 0. So this time is 0, which means that the GX is actually the minimal value. And this saying that X star is the minimal value of the G function. Does it make sense here? So if you have an X point here, and you find out that no matter you go into which directions V, you cannot find any values is smaller than this one. Then this is the minimal values on the whole space, right? In the whole space. Does it make sense? So this is because now you find out that for any vector V, you cannot find any, in any directions, you cannot find any points that is smaller than this one. So now this is the smallest values of the GX in the whole space. Does it make sense? Any question? Any question? No? So this is just the direction one if we assume this one is the solutions of the AX. And another directions is we assume that this is the minimum value of the GX. Assume X star is a vector that minimize the function G, that minimize the function G and then let's go back to here. So because the X is the minimum value, so this one it should be, so which means that this is the minimum value, and then along this line, and then this one it should be the smallest number, and this means that we have, so because this is the minimal value, and then GX star is always smaller than or equals to the GX star, no matter what the T hat it is. And then we still have this one, this number should be greater than or equals to the number we have here, because we assume the X star is the minimal value. So now, but by the equations we get there, and actually we should have this number is more than or equals to this one. But now you are saying this, which means that we only can do this when this one equals to 0. So from there we have, but from the equations, let's say this is the equations 1, we have GX star is always equals to or bigger than the gx star plus t hat v. And you would see this because we have this number is smaller than or equals to this one, and this number is bigger than or equals to this one. And this gives us that the gx star is actually equals to the gx star plus t hat v, right? And from that equations, it also means that, so now you have this one equals to this one. And this means that this one should be 0. And if we want this one to be 0, and then the only possible case is that this one is equal to 0 for any vector v. This means that v and then bax star m equals to 0 for any vector v. So now, could you conclude that b minus ax star equals 0? Can you do this? And then why? So the question is that, could you do this? And then why? And then this is the question for you. And any idea? You could use the property of the inner product here. So here you have b minus ax star equals 0. And then so we have ax star equals to b. And then so we can conclude that the x star is the solution of the ax equals to b system. So, but why do we have this? Any idea? Any idea here? Why can we do this?
Because we cannot be 0. And the production they're not counted.
Because we cannot be 0, right?
Yes. And in the product equals to 0, so the b minus b is extraction.
Yes. So you mean that you are letting the v to be b minus ax star, right? Not really. Yeah. Okay. Never mind. So that's a correct direction because the v, but here the v can be anywhere actually. But it's the correct directions because we should focus on the series property here. And so now let's let the v to be b minus ax star. And then what do you have here? So let's go back to the property of the inner product, okay? The property of the inner product here, x inner product with x equals to 0, if and only if the x equals to 0. But now we just let the v equals to the a v equals to the b subtract the ax star, right? So this gives us that b minus ax star, and then inner product with b ax star, that is the same things, right? And then it equals to 0. And then from that property, and then we get b minus ax star equals to 0. Does that make sense? So this is just the property is from the property of the inner products here. So this is very important. And now we have proved both directions. If ax is a solutions of the linear system, and then it's a minimal value of g. And then if this minimal value of the g, and then we have this one should be the solution of the linear system. Any questions here? So we separate the proof into 2 parts, and then the first part you have calculated how to get the minimal values along these directions. And after we get that one, and then we prove that the both directions here. Any questions? And this is the proof. And it's pretty important in the conjugate gradient theorems. And next, okay, next, let's see. So before we go to the conjugate gradient theorems, and let's see, what do we have here? So actually, we want to introduce two things. One is the steepest descent, and then the other thing is the conjugate descent. So if we have only 7 minutes left, and then let me just briefly introduce to this one. So for the steepest descent, it means that it just go to the gradient directions. And you could see steepest descent here, right? And then another name of this is the gradient descent. And if you take a look at the, if you have taken the multivariables calculus, and then you would know that the gradient is the fastest way for the functions to increase. And so if you are going to the gradient descent way, which means that you are going to the fastest descent way of the function. And also the gradient is always orthogonal to the contour here. This is the contour of the gx function. And the gradient, you can take a look at the green part. The gradient is going into this way. So it's orthogonal to the contour here. And then so it arrived to the minimum point along this direction. And then how does the gradient descent choose the next direction? And then it chooses the next directions based on the contour here. And then it's just go orthogonal to this contour. And then that is another one. And then for this point, and then it also goes to orthogonal to this contour, and then this one. And this is the gradient descent method, but we will introduce this into details in the next class. But the things nowadays we are doing this one, the conjugate gradient methods. The conjugate gradient methods is not orthogonal to that contour here. It's actually orthogonal. It's something about the matrices we have here. It's orthogonal. We say the directions are orthogonal. And the best things about the orthogonals or the conjugate gradient method is that you will see, okay, this is the 2 dimensions function, x and y, and then there's some contour here. And you will see this is a 2-dimension problem, right? And then if you want to minimize it, how many steps do you need to take? How many iterations do you take to arrive this minimum value? So it just go once, and then change the direction, and then 2. So if you have an n dimensions problem, and then it would arrive to the minimum values at most n steps. And that's the good things about the conjugate gradient. And if you take a look at the gradient descent, just gradient descent, conjugate, it means that this conjugate gradient, it means that it's related to the A. But here, the gradient descent is not too much related to the A matrix. It's just going to orthogonal to the contour here. And you will see there are several, we take several iterations to arrive to the minimal value, which means that we have a slower convergence rates for the gradient descent. Does it make sense? Any questions here? And this is just a brief introduction into that gradient descent and conjugate gradient descent. And nowadays we would use the conjugate gradient descent and not the gradient descent. That is a slow method. So next class, and then I will tell you that how we determine the gradient descent direction and how would we determine the conjugate gradient directions. I think we can have some early release today, 3 minutes earlier than the design end time. So if you have any questions, and then you can come over to here. And then today we just briefly to mention one very important theorem here. Next class, we would use this theorem and this t hat value to get the conjugate gradient algorithm. Okay, and that's it. We get the homework on Thursday, and then it's due by next Thursday.